So hi everyone and welcome to our weekly ALPRN seminar. The speaker today is Ángel Alonso from TU Graz, and he's gonna tell us about a new approximation of the multicover.
Thank you, Sarah, for the introduction. So yes, the topic of today I want to present is about the multicover and a new construction that approximates it. So the starting point I want to start with is the union of balls. So this is very simple. We are going to work with a finite subset of some, let's say, Euclidean space or some RD. And then the union of balls of X for a given radius R is just given by replacing the points by some ball of radius R. Yeah. So for example, here we have this X kind of resembles a circle, and okay, we just replace the points by balls. And of course, the important thing here for us is that, well, this union of balls assembles into a filtration. What do I mean by filtration? Well, for each parameter, for each radius, we are going to have a topological space, in this case, this union of balls for a given radius. So the picture is as follows. Here we have the real line, and for a point, yeah, we have the topological space of, well, in this case, small balls around these points. And importantly, as we increase the parameter, as we increase the radius, then we have inclusions. Yeah? The union of balls with a small radius includes in the union of balls with bigger radius. So this is the filtration. And of course, filtrations as here are a fundamental object in what we know as persistence. And I say persistence meaning, well, how long do topological features persist through parameter space in a filtration? So here, for example, these points that are arranged in a circle, at some point, the union of balls will recover the circle, will also be a circle. It's a topological space. And then as we keep increasing the radius, well, at some point, the circle will be covered completely, will disappear. So this circle will persist for a range of radii. So we look for how long, how little, or how much, how do these topological features persist? Okay, this is just the starting point. And then one might wonder why the union of balls. Well, as we have kind of seen, it captures the topology of this finite point cloud at different scales. It's also a fundamental object in manifold reconstruction. By this, I mean that imagine that we have a submanifold in some RD, in some manifold of Euclidean space, and then we are given some samples of it. Well, just by replacing the points by balls of a given radius under some conditions. I saw here like an example paper. We can recover the submanifold. And then it's stable to perturbations, something that perhaps you can imagine, and which is captured in the stability theorem. And then it has many applications. Perhaps I don't need to say this here. There is even a database of applications. So this is why the union of balls. It also has a simple definition. But then perhaps why not the union of balls? Why not the union of balls? Well, one reason is that the union of balls is not robust to outliers. And this can be seen here. Well, before we have these points arranged in what looks a circle. And the union of balls is kind of effective, of course, to recover the circle as we see here. But now suppose that we add 3 outliers. I'm going to add like 3 points here. And now the union of balls is not going to recover the circle. Yeah, because at this radius, well, these 3 points are going to cover the center. Perhaps it recovers this circle, but not the whole circle. So in this sense, just by adding 3 points, all our construction breaks down. This is, of course, a problem that, well, has been known and treated, and many solutions have been proposed. I just list here a few of them. We can filter by density. Let's say just we estimate the density of each point and remove the outliers either manually, or we include another parameter just to handle them. We can also do subsampling. There is some other constructions like the regrips. I will talk a bit about the regrips and some others. And many of these solutions have already been applied in practice and with success. But today I want to focus in one solution. And this solution is the solution of the multicover, perhaps related to this probability approach, with this approach of Chazal and co-authors of taking not point sets but measures, and also introduced by Siki. And this will be, as we will see, an extension of the union of balls. Okay, so this solution has at least two advantages, as we will see. First, it's going to be choice-free. What do I mean by this? For example, in filter by density, when we filter by density, we need to choose how are we going to estimate the density, and that will involve, well, the method and also the parameters. And it's also robust to outliers in a specific theoretical sense, and we have this stability theorem by Plumber and Lesnick that I will also talk about a bit. So in this sense, well, again, it's choice-free, kind of like the union of balls and robust to outlier as we want, but there is a price to pay. At least we have to pay with two things. The first one is that, well, this filtration is going to involve now two parameters, not only one as the union of balls. And the other problematic aspect is that, well, there is currently no practical implementation that can handle more than a few hundred of points in low dimensions. And this is kind of the objective, the research directions that we are taking here. We will eventually want to compute the multicover efficiently in practice. Okay, so what do I mean by multicover? So again, I'm going to fix a finite subset of RD. And then the k cover of X now is going to depend on two parameters, the radius and then some order K, I call it order. And then the K cover for this radius and this parameter K is going to be the set of points of ambient space of RD within distance R of at least K points of X. This can be understood that, well, as the points covered by at least K balls. Yeah, so here I show a bit of an example. If K equals 1, the one cover is just the union of the balls around X. In this sense, it's an extension of the union of balls. And if K equals 2, well, the 2 cover is just the intersection of two balls around points of X, like I saw here. So this will be the 2 cover, this little cross. And we can continue, K equals 3, this is just the intersection of 3 balls, and so on and so forth, right? This will be the picture, this little wedge for K equals 3. And of course, now we also have a filtration, in this case, a bifiltration over two parameters. What do I mean by this? So here I have drawn these points arranged in a circle, and I have tried to make it as hard as possible for the union of balls to recover this circle. I have added like a grid of outliers here. And you can see here on the right, if I take K equals 3 and a small radius, this will be the intersections of all 3 balls. And then, well, I kind of recover the circle. Here with K equals 2, I also kind of have some circle here. And K equals 1 is just the union of balls. And of course, there is an inclusion. If I reduce K, I have an inclusion. This includes here and so on and so forth. Right? So in this per row for this parameter, I have a filtration. And also I can increase the radius. And going down, I also have inclusions. Here I have increased the radius and so on. So perhaps you can see already here that the multicover is robust to outliers. I have added all this grid of points, and well, for some parameter, and this radius, I can recover the circle. Okay. So let me tell you a bit more about why is robust in which specific sense. First, I'm going to normalize the K cover. So now the parameter is going to be the radius and also some density parameter P instead of K. And P goes from 0 to 1. Then I take this normalized multicover for the parameter R and P is going to be the set of points of RD within distance R of at least P times the number of points in X, points of X. Yeah, so P is, well, a point is here if is covered by at least some percentage of the balls around points of X. And now there is a very simple observation. Well, we fix X again, and suppose that we add some outliers. I denote them by O. So here is the picture. The points will be as before around the circle, and then I have added these 3 outliers. The observation is as follows. If a point is covered by K balls around points of X union the outliers, around all points, then it is covered by, well, K points minus the number of outliers we have added around points of X. What does this mean specifically? Well, it means that we have this inclusion. Yeah, if the multicover of X union the outliers for some parameter K is included in the multicover of X, and we just need to subtract in this parameter the number of points of outliers that we have added. And when we normalize, we have this inclusion, or it can be seen that we have this inclusion where, well, the parameter P, we just need to reduce it by, well, this percentage of points that we have added, the ratio of outliers over the total points. So in a way, this multicover over all these points is close to this multicover as just the points of X without the outliers. And this can be formalized better, and in a way follows from the stability theorem that I was speaking before. And I will write it here for some distance between bifiltrations, and this will be the interleaving distance. Then the distance between the multicover over X and the multicover of X over the outliers is not too big. If we add outliers, then the distance cannot increase too much. Just at most the percentage that we have added of outliers. And of course, the evidence, because I won't be defining the interleaving distance, the evidence or the picture is again this one, yeah, that we can discover we can recover the circle here. So now, hopefully I have convinced you that the multicover is at least interesting. We want to compute it, and by computing it, we need a way to get it into a computer. And the best way to do that is, well, just obtaining some combinatorial object. So we want to obtain a combinatorial model of the multicover. And by this, I mean that replacing its topological space by a homotopy equivalent simplicial complex with some other technical conditions, but we want to replace the topological space by simplicial complexes. And of course, we want this combinatorial model to be as small as possible, where small and the size just refers to the number of simplices that we have. And this is, of course, with the objective of trying to compute it in practice. And this is against the current implementations. There is one implementation by Osang, handle around 200, 300 points in low dimension, in low dimensions 2 and 3. So this is kind of our objective, trying to compute this in practice. Okay, and this of course has some history. It starts in 2013 when Sihi proposes the first combinatorial model that has an exponential size on the number of points. So in this regard, it's perhaps unfeasible to compute it. Then, well, there has been also approximation proposed. This is by Lesnick and Wright. They propose the degree bridge, which is a square root of 3 approximation of polynomial size. Brunner and Osang also, well, tried to compute the multicover and succeeded for computing slices for fixed R and fixed K. And using higher order Voronoi diagrams and some techniques related to the Delaunay triangulation. And then Corbett, Kerber, Lesnick, and Osang in 2021, they using this work of Brunner and Osang, they have a polynomial size combinatorial model of the multicover. So now we are in polynomial. Then Bouchet, Dornelas, and Kerber, they have a 1 plus epsilon approximation of exponential size. But when fixing k, this is linear on the number of points. Here, the number of points is n. So in general, k is going to be of the order of n. Well, it depends, but at least it's linear when fixing for some fixed k. And then most recently, Lesnick and McCabe has proposed a 1 plus epsilon approximation of not of the multicover of the subdivision groups, which is closely related, and this works for general metric spaces. I will be speaking about this later too, of polynomial size. And the approximation that I want to talk about today, the one that is in the title, is about a 1 plus epsilon approximation of the multicover of linear size. So the rest of the talk, I will be speaking about some techniques that go into proving this theorem. So first, let me state the theorem, perhaps more formally. So we fix a finite x subset of Rd, and then we fix an error parameter epsilon. Then the theorem says as follows: there is a filtration S of subsets of Rd that 1 plus epsilon approximates a multicover. What do I mean by this? Well, if we take the multicover at some radius r, then this is included in this filtration S just by increasing the radius a little bit. We have an inclusion in 1 plus 3 epsilon times r, and vice versa. If we start with this filtration S at some radius r, then we have an inclusion in the multicover just by increasing the radius just a little bit, 1 plus epsilon times r. And then, well, this filtration S has a combinatorial model of linear size and the number of points. And this result should be compared against this other result of Cabana, Jahanser, and Sikhi that is analogous. So this result can be considered an extension of this one. That says the same, but for the union of balls instead the multicover. It says there is a filtration S, again of subset of Rd, such that, well, just by increasing the radius, 1 plus epsilon r, we have this inclusion. And, well, this is slightly better. We don't need this filtration S, is just included in the union of balls. That also has a combinatorial model of linear size. And some ideas that go into proving this theorem, or rather the approaches are very similar, and this theorem inspires this theorem. So this result of Cabana, Jahanser, and Sikhi, it's more general. It applies to general metric spaces and Vietoris-Rips complexes. And it's an extension of this previous work of Sikhi about a linear size approximation to the Vietoris-Rips filtration. And the techniques that are now included under this term, sparsification, have also having some influence in approximations of the Delaunay filtration. And some of these techniques have also been used in the context of the multicover in this previous work that I mentioned before. So now I will talk a bit about the techniques of this work and how they can be extended to the multicover. Okay, so first, a bit of a geometric intuition. What is the geometric idea, or one of the geometric ideas of this work? The first observation is that for a large n of radius, balls are approximately the same. Well, if you look at these 2 points for a small radius, these balls look very different. But when the radius is big, well, these start to be from afar, they start to look the same. More formally, like just pick any 2 points, x and y, then there is going to be a large n of radius such that the ball of radius r around x is included in the ball around y of just a radius just a little bit bigger, meaning 1 plus epsilon times r. So perhaps the motto, the philosophy behind this is that, well, for large enough radius, we do not need all the points of X to approximate the union of balls. Many balls will be similar to each other in this sense. So how do we exploit this? So Cabana, Jahanser, and Sighi, they propose the following. We are going to work with a version of balls that are frozen. What do I mean by frozen? Well, at the start, meaning that it's small values of the parameter r at small scales, they are going to be normal balls. They are going to have radius r. This will be depicted here in this picture. These balls around these 4 points, they have all the same radius. At some point, at certain scale, some balls are going to be frozen. They are going to be, they are going to be not growing anymore. The radius is going to be constant, as you can see here in this picture. So here we have, again, 4 balls, but this one has been frozen, it's not growing anymore. And this other one next to it is catching up to it and is starting to cover it. So now once this ball has been covered by this other ball, well, just to preserve this special union of balls, we can just remove this frozen ball after a certain radius. And this will be the picture. For large radius, we just have 2 balls. We have removed 2 of them. Yeah, so maybe to say it again, we have this version of balls, and instead of always having radius r for scale r, they have radius r. Well, at some point they stopped for a while, and then they disappear. So now a very visual approximation is, instead of what I was just saying, instead of the union of balls, we just take the union of these frozen balls. And I have taken these pictures from this video of Cabana, Jahanser, and Sighi, which is great. And you can see here the union of balls, of many balls. And here you can see, well, we have here in blue frozen some balls. And you can see that these are kind of the same. And as we increase the radius, well, some other balls will be frozen. And then if we increase the radius more, some balls will be removed. And of course, here we have less number of balls. So for the multicover, or in this approximation, we are not going to freeze balls completely. We are going to slow them down. So what I mean by this is that the radius is going to be r as before at the start, and at some point the radius is just going to be just smaller than r. The balls are going to keep growing, but just slower. We don't freeze them completely. This will be the same picture will apply. Then this is not very important, but it has a technical advantage, is that, well, balls that grow slow, forgetting for a moment that they may disappear at some point, balls that grow slow, eventually they intersect. And this is different from just freezing them completely. If we freeze them, then they won't intersect in general. This is just some technical point. So now I will be speaking about balls that slow down. And now if one goes back to the definition of the multicover, one sees the additional parameter k. I have been speaking so far about this technique, about the union of balls, and the question here would be, how do we extend this to the multicover? How do we incorporate these additional parameters? And what we are going to do is we are going to, well, consider weighted points. Now the points are going to have a weight. So at each scale r, the weight of a point x is how many points it covers. I'm gonna define what I mean by this covering relation. At the start, for small scales, each point covers itself. It has a weight of 1. This will be the picture here. And remember that we slow balls and then we remove them. So when the ball around x disappears, its weight is transferred to its nearest neighbor with non-sloped ball, in this case y. I depict it like this arrow. So now at this point, y has weight 2. It covers itself, and it covers also x. So in general, when the ball of a point, let's say y, disappears, the weight of all points that y covers at that point are going to be transferred to the nearest neighbor with non-slope ball. So here, in this picture, the ball of y has disappeared, and y was covering itself, and it was covering x. So x just looks for its nearest neighbor, which is going to be this point, and y looks for its nearest neighbor, which is again this point, and well, the weight is transferred. So now this point has weight 3. So in this way, for each radius, we have a map. I denote it by CR. This will be called a covering map with the following semantics. X is sent to y if, well, X is covered by y according to these rules at some radius R. And now if we go back to the definition of the multicover, well, what was the multicover? It was the set of points of RD containing at least k balls of radius R around point of X. And we have, well, done 2 modifications. We are now using balls that slow down and eventually disappear. And then we are taking weights. So now the filtration that we want to consider, the definition, hiding some technicalities, it will be the set of points of RD containing a subset of balls that might be slowed down, whose sum of weights is at least k. So now one ball might count as, well, as many balls as it has as weight. So then this would...
Can I interrupt you for a moment?
Yeah, sorry. Yeah, for sure.
If you could go back to the slide. I have a question. I think I know the answer, but just to make sure, because there's also weighted Delaunay triangulations, right? And this is now a definition of weights in a context that is similar to the Delaunay triangulations, but it's not the same weight, right? I should not think of it as similar at all.
Yes, right? you shouldn't think of it as weighted Delaunay triangulation. Yeah. Yes.
Okay.
Yeah.
Thanks.
So maybe it helps for your intuition, think of this slowing down or this freezing as adding some weight in the Delaunay triangulation. This is also something that Sigrid does, at least in the paper of the sparse Delaunay. But no, this is independent. Yes, good point. Thank you.
Thank you.
So, okay, so then this is some ideas that go into, well, this filtration S in the theorem is defined as I have explained with the slowing balls and the weights, and then one would need to prove that all these inclusions hold. But now I want to focus on what is this combinatorial model, what is this combinatorial model about, and I want to give you some ideas. And this is based on the barycentric subdivision following the multicover Nerf theorem and a construction of Sighi that we will see. Okay, first, the model of the union of balls. Yeah, so now again, fix a finite X. Now the check complex for a given radius is the simplicial complex given by as follows. The vertices are going to be the points of X, and then we are going to have an edge. This is the picture. If 2 balls intersect, then we have an edge. So here we have this little wedge, and so on. If 3 balls intersect, like here, we have a triangle, and so on and so forth. So the check complex is the nerve of the union of balls. What do I mean by nerve? So take a finite collection of sets, C, then the nerve of C is the simplicial complex, well, constructed as I have just described. The vertices are going to be the sets, and then we have edges if 2 sets intersect, and so on and so forth. Then we have the Nerf theorem, that it goes back to the 40s, and there are many variants. I'm just going to focus on this one. If C is a finite collection of closed and convex subsets, as the balls that we are considered are, then the Nerf is homotopy equivalent to the union of the sets. So as a consequence of this theorem, this check complex that also assemble into a filtration, this will be the picture, is a combinatorial model of the union of balls. By this, I mean, well, we have here a homotopy equivalence under some technical conditions, in particular, these square commutes. So the union of balls filtration is homotopically equivalent to the check filtration, and we say that, well, it's a combinatorial model. Okay, so this is again for the union of balls. How do we extend it to the multicover? This is when the work of Sigi comes in. And so what we are going to do is we are going to subdivide the check complex. What do I mean by subdivision? So let S be a simply subcomplex. Then its barycentric subdivision has as vertex set the simplices of S, and M simplices are going to be chains of simplices. And perhaps it's better to look at the picture. Here I have S, this is just a triangle. And here, since I have an edge, well, I add a vertex that represents this edge. I have a triangle, so I add this vertex that represents this triangle, and then I connect everything together. And then the observation is that, well, this subdivision is also filtered over a parameter K, just about the cardinality of the minimum element in this chain. And again, the picture for K equals 1, this is just the whole subdivision. For K equals 2, this is the subcomplex spanned by those vertices that come from edges. And we will obtain this in this case. And for K equals 3, well, this is just the subcomplex spanned by those vertices that come from triangles. And then when we subdivide the check complex, well, the check complex is parameterized over R. Then this yields a filtration over R coming from the check complex and K coming from this subdivision. This will be called subdivision check. So here we'll have a little example. Here we have 3 points, and the check complex will be this triangle. And then you can see, perhaps proof by picture, some intuition that, well, we at a point that will correspond to this intersection, a point for this intersection, and so on. And finally, a point that corresponds to this intersection. Okay, this is a division check. Here is another picture. And the multicover theorem, it says, well, this subdivision check by filtration is a combinatorial model of the multicover. These are ideas of Sigi. So now we have this theorem, which is key. And well, instead of, if we replace check by RIPS, then we also obtain a bifiltration. This will be called the subdivision RIPS as a version of the multicover for general metric spaces. I won't discuss this further, but just to note about this extension to general metric spaces. In general, I'm talking about subsets of RD, but many of these ideas work for general metric spaces. Perhaps under some technical conditions. Yes, so now how do we extend this to our version of the multicover, of the multicover? So well, we just adapt it. Instead of balls, we are going to consider slow balls, these things that we have seen. Now remember that we have weights, so we can just consider in this theorem a ball of weight K as just K copies of the same ball. And then there is a trick that we used for everything to play nicely, for everything to be a filtration, since we are removing balls, and we just lift everything 1 dimension higher with the use of cones. This will be the picture, and I won't talk too much about this. But the point is perhaps that to obtain a combinatorial model of this version of the multicover with slow balls, to obtain a version of this theorem, we just adapt this multicover theorem of Sigi. So I have been talking about, a bit of this part of the theorem, a bit of this part of the combinatorial model, and now let me talk about a bit the size bounds. Why is this linear? And this will follow by some packing arguments, and this is also ideas coming from this paper of Cabana, Yafansera, and Sigi. So one thing to note is that these points for a given radius, some points are still present. Some balls have not disappeared yet. Some balls are non-empty. This subset of balls is going to be well packed. What do I mean by this? For any 2 such points x and y, well, they are going to be at least this distance apart. Some constant c that is going to depend on epsilon times r. Yeah, and this is going to follow by construction. And to do this construction, we are going to use what is called a greedy permutation. So I write here the set of points with non-empty ball are going to be a prefix set of a greedy permutation. What is a greedy permutation? I will show a picture soon. A greedy permutation orders the points of X such that each successive point is the farthest away from the previous points. And then there is a very nice greedy algorithm by Gonzalez that says just start with a random point and just keep picking the farthest point from the previously selected points. So this can be computed in n log delta time, where delta is the ratio. This is actually called the spread of the input, is the ratio of the largest to smallest distances on the input. I won't go into details here, but there is a lot of literature about computing greedy permutations, including some recent work by Chovetsi and Seth in these topics. Perhaps the bottom line that I want to transmit is that it can be computed fast. So what do I mean by greedy permutation? Here comes the pictures. Okay, just let's suppose that we want to compute the greedy permutation of this point cloud. We'll just pick a random point. Then we are going to look for the farthest point from this point. It's going to be this one. So now, well, the greedy permutation is first this one and then this one. And now at the farthest point from these 2 points, it's going to be this one. This is the point that maximizes the minimum distance to any of these two. And then we add it. This will be our third point, and we continue until we have gone over all the points. And now, well, each prefix set of this greedy permutation is a net. And I'm going to define a net now, but just maybe as an intuition, you can think of this as a set of representatives at a given scale, set of representatives of this point cloud. So give me a radius R, then I say that, or we say that a subset S is an R packing if all points in this subset are at least R apart. And then a subset is an R net if it's a maximal R packing. Yeah? There is no other R packing S prime that contains S. And in the greedy permutation, we have been computing exactly this. Well, one point is an R net for a big R. This is just an R packing, and you cannot add any other point for this to keep being a packing. It's maximal. If we keep decreasing R, at some point, just this point, it won't be maximal. We could be at this point, so we add it. So these 2 points at this point for this radius R are an R packing and maximal in that way. So we could keep doing that. So we have a nested sequence of maximal R packets. And this is what eventually is going to give us these packing properties. We are going to slow points, we are going to slow balls according to these prefix sets. And well, then we have seen that the size of these complexes depend on how much all these balls intersect. And there is a lemma that we can say, well, if these slow balls intersect for some radius, then not a constant, at most a constant number of balls are going to intersect at a given time. And this is what eventually gives us the small size, the linear size. Okay. So I have been talking about this theorem, about the approximation of the multicover, and the techniques, some ideas about the techniques were just slow balls down, remove them, and keep track of the weights, following this work of Cabana, Jacasser, and Sifi with weights. Then there's a combinatorial model based on the subdivision, and then use greedy permutation nets. And so this is my last slide. Since this will be on YouTube, there are some videos also of the channel that go over some of these ideas. I have taken some prints of this video, visualizing sparse filtrations, HD. There is a nice talk from Mike Lesnick on some of these ideas, and there is also Tom Coughley's Coco line in some of these ideas too. And that's it. Thank you.
Thank you so much. So before we get to questions, maybe I would ask everyone to unmute themselves so we can give a round of applause for the speaker. And now, it's time for questions. So feel free to just ask a question, or if you want to raise your hand, and I'm going to call you in order, whatever you feel most comfortable with.
Yeah, one question. Very nice talk, by the way. I really liked it. Yeah, my question is, you said right at the beginning that the reason why you don't let balls freeze, but instead you let them grow slowly, is that they will still be able to intersect with each other eventually, just slower. But then I think I missed a bit the point where this later becomes relevant. Like, so maybe can you say a bit more about why you need to let balls become slower instead of freezing them?
Yes, good point. Yeah, because perhaps I didn't speak too much about it. So let me go to this slide of the slowing balls. Thank you for the question. So this relates to this work of yes, I was speaking about this work of Bouchet, Dornelas, and Kerber, and they freeze the contraction works with freezing. And that gives you some problems when computing that they solve by just taking how to say small increments. Everything works the same asymptotically, and so slowing balls down was a solution to try to address that. Perhaps everything works with freezing, but slowing balls down and with a specific rate that is kind of quadratic, as I saw here, allows you to compute the intersection time exactly instead of taking discrete snapshots of the filtration.
Yeah, thank you.
Further questions for Ángel?
I have one.
Go for it.
Sorry if you already said that, but so what is the ratio with which you slow them down? How do you choose that?
Yes, okay. So the ratio is kind of drawn here. It's technical. It's just for everything to work, the proof to work. But so it has to be between these two lines, these two blue lines. So this gives you some wiggle room to try to choose this function that's as long as it's between these two lines, everything would work. And some of these functions that you take here, I claim that are better or perhaps have some more efficient computation than others. So, but to answer the question is just for, I choose it just for everything to work.
Okay, thank you. Further questions? Okay, so if there are no further questions, then we're going to take the rest offline. So Ángel, thank you again. I'm going to stop the recording. Yeah, thanks so much for coming.
Thank you.